From space, the Earth is defined by its water. It covers 71% of the surface, creating the familiar blue marble we've used as our baseline for a habitable planet. For decades, the consensus was that early Earth was entirely dry. The accepted timeline suggested that this massive volume of surface water arrived over millions of years, delivered by icy comets and asteroid impacts. But between 2025 and 2026, researchers mapping the planet's interior located a massive reservoir of water buried within the mantle, shifting the focus from cosmic impacts back to the Earth itself. This chart compares known planetary water volumes. If you measure every drop from every surface ocean and sea, the subterranean reservoir is significantly larger. Current estimates indicate this deep mantle layer contains up to 3 times more water than all surface oceans combined. Finding that much water inside the planet changes the mathematical models of our origins. It suggests our oceans likely didn't arrive from the sky, they were squeezed out from the deep Earth. When we talk about an underground ocean, it's easy to picture a cavernous, liquid sea. But at the extreme temperatures and pressures of the mantle, water cannot exist in a free-flowing state. To map a zone humans can never physically visit, geologists used earthquakes as a form of planetary sonar. Every time the crust shifts, it sends seismic waves rippling through the planet's interior. Researchers monitored how those waves traveled and noticed a distinct pattern. As the seismic waves crossed specific regions deep inside the mantle, they exhibited a sudden, measurable drop in speed. High-pressure laboratory experiments confirmed that the only physical explanation for this exact velocity drop is the presence of massive quantities of water trapped within the rock. By tracking the tremors of the planet, scientists were able to identify a reservoir that spans the entire globe. The mechanism holding all this moisture is a specific mineral forged under intense subterranean conditions, known as ringwoodite. Under crushing pressure, ringwoodite acts like a solid, crystalline sponge. It absorbs surrounding moisture, locking water molecules directly into its microscopic geometric structure. This water isn't permanently sealed. Over millions of years, as rock layers heat and shift, the mantle effectively squeezes the sponge, forcing that trapped moisture upward through microscopic fissures. As this water migrates, it softens the rock, provides lubrication for the movement of massive tectonic plates, and creates the volatile pressure that fuels volcanic eruptions. This continuous upward migration shows that the Earth is an active inside-out water cycle. This slow release of deep mantle water is what has maintained our surface oceans and climate over billions of years. Mapping this plumbing system also provides a practical tool for modern geological safety. Because water reduces friction on fault lines, identifying high moisture zones in the mantle helps geologists better model where tectonic stress is building and which regions are most susceptible to future tremors. If this internal mechanism operates inside other rocky planets, the search for life extends far beyond a planet's surface. Mars appears as a dry, desolate wasteland, but beneath that exterior, similar internal reservoirs could still exist, trapped within its mantle rock, just as they are on Earth. We can apply this theory to the icy moons of the outer solar system, like Jupiter's Europa, where internal heating may sustain hidden oceans beneath the frozen crust. We see evidence of this internal pressure on Saturn's moon, Enceladus, which actively vents water vapor plumes from its interior into space. Finding an ocean locked inside solid rock reminds us that a planet's surface only tells a fraction of its story. It suggests that the search for life should not stop at the crust, but look deeper into how planets store and cycle the